In this video, I want to consider delta functions for representing signals, images, or indeed any function that's of general interest in science and engineering. So this is relevant to digital signal processing, quantum mechanics, imaging, medical imaging, and it also really helps with understanding a really crucial concept, that of analysis and synthesis, which is very helpful for understanding Fourier analysis. So this is the problem that we're dealing with in this video, which is how do we express these kinds of medical images, or indeed audio waveforms, or voltages from electrodes, or indeed natural images, or quantum mechanical wave functions. How do we represent these in a mathematical way that allows us to manipulate, process, and work with these kinds of signals and images? And this is where we'll be talking in this video about how to use the concept of basis functions, and in particular the Dirac delta function, or generally the delta function, in order to represent all kinds of diverse signals mathematically. Okay, so first of all then, the concept of a basis function. This is really talking about using a simple parameterized function, and we'll see those parameters during this video, such that we can use those building block basis functions in order to synthesize more general functions, such as audio waveforms or indeed brain images, for example. And this video will all be about the delta function in the continuous version, known as the Dirac delta function, named after Paul Dirac, or indeed the discrete version of the delta function, sometimes called the Kronecker delta, a special case of that, named after another mathematician, this time a German mathematician, Kronecker. And from that we get the unit sample function, also symbolized with this delta function. But notice the difference here. When I'm talking about continuous functions, I'll be using these regular brackets here, and I'll be using square brackets when I'm dealing with discrete functions. In other words, where the domain of the function is now an integer rather than a continuous real value. So to be clear then about that, if we've got a continuous function f of x, I'm using these brackets here. I'm saying that x is an element of the real line. It's basically a real number that goes in to this function to deliver some function value f. And you can see here I've been using these kind of spike-like arrow functions here, which are the delta functions that we'll be explaining in this video, in order to synthesize this continuous function. So that's for the continuous case. And for the discrete case, it'd be very similar, except of course I've now got those square brackets. So I've now got an integer value for the independent variable x, and here we've just got a sequence now of samples, if you like, for a discrete function, such as, for example, an audio waveform. Okay, so to deal with understanding the delta function, I'll start off with the Dirac delta function, and to get to that, we'll start off with the well-known Gaussian function, or the normal distribution, which is used in statistics. So this is named after a German mathematician called Gauss, and just to really rapidly understand what's going on with this function, I'm going to plot it out here, just build it up in a very simple way. By starting off with a linear function, so this is just sort of y equals x, or here p of x is equal to x, and so that's just the identity line, very straightforward. And now to get towards the Gaussian function, first of all, we recognize that what we can do is shift that function. This identity line can be shifted to the right by some distance mu, and this of course is just the y equals mx plus c, just a regular linear function where the gradient is 1 and the intercept is minus mu. So mu is going to in fact be the mean of the Gaussian function, or the normal distribution. So I'm just building it up in a very simple way here. So we've got identity with a shift, and then what we can do is square that, and so what we see now is we get the familiar quadratic or the parabolic looking function here. So it's just x squared, just shifted to where x is equal to mu. Then what we could do is change the amplitude of that by dividing by some constant value, 2 sigma squared. Sigma squared is the variance of the Gaussian function, and it controls, as we can see here, how broad this function is going to be. So if we didn't have it, we'd have, for example, a parabola looking like this, whereas if we now divide by some large value, then what happens is the values broaden out. And of course we could narrow it by dividing by much smaller values for the variance for sigma squared. Then, of course, as we know, hopefully you already know where we're going with the Gaussian function, we take the negative of that, so that's just going to flip that, mirror it in the x-axis. And then we take the exponential. Now already we can see the very familiar bell curve that is the Gaussian function or the normal distribution. But because we need the area under this curve to remain a total area of 1, because this is going to be a probability density function, we're going to need to normalize that. And so we're just saying, therefore, scale it by this in order for this integral to equal to 1, the area under this Gaussian function. So that's the basics of a Gaussian distribution. So it's got some variance, sigma squared, controlling the width of the function, and it's centered at some value x is equal to mu. Now we're going to use this to get to the continuous Dirac delta function. And first of all, though, just to show a bit more of the parameterization of the Gaussian distribution, you can see here I'm showing it for different values of sigma squared. So this is a small sigma squared, so it was a very sharp peaked Gaussian, and then as we increase the variance, so this gets broader, and the amplitude goes down because we require the area to remain equal to 1. And then here you can see what happens if we use a value of mu equal to, for example, here -2, that shifts the Gaussian to x is equal to -2. And also, of course, we could use a value of mu equal to 2, and so x minus 2 there would give rise to a shift of that Gaussian to the right. Anyway, so what we're going to do now is just see how this leads us into the Dirac delta function. So there, first of all, is the Gaussian that I've just talked you through. What we're going to do then is set the mu value to be equal to 0, and I was going to consider a centered Gaussian, one where x is equal to 0 is the peak of the function. And then we're going to look at the limiting case as the variance, or here just the standard deviation, the square root of the variance, tends to 0. So I'm just going to plot that. First of all, I've just shown it here with mu equal to 0. And then here on the right hand side, you can see what happens as sigma tends to 0. So it starts off broad, and then as sigma tends to 0, so this function gets narrower and narrower, taller and taller, but of course the area needs to remain equal to 1. Okay, and then what happens as it tends to 0, so we represent it with this arrow, this kind of delta function as we'll be calling it, because this is effectively shooting up to infinity as the width now is infinitesimal. So to characterize that, we're saying this is the Dirac delta function named after Paul Dirac, who used this in a quantum mechanical context. Again, we've got the area of the function still equal to 1 as would be expected, but now when x is exactly equal to 0, when the argument of the delta function is 0, then the amplitude is now plus infinity, and then when x is not equal to 0, in other words elsewhere, then the function is equal to 0. So this is the rather odd Dirac delta function. Okay, we can shift this function around, which is going to be very useful, just like we saw that Gaussian shifting around by changing the value of mu. So what we can do here is change mu to be equal to a, and we can define our Dirac delta function, delta of x, shifted to where x is equal to plus a now. And that's just going to look like this. That's just delta x shifted to plus a. And so we know that it's the minus a is going to shift it to the right because we've seen that already for the Gaussian breakdown that I went through earlier. But if in doubt, you can just plug in a value of x is equal to a here. Then you've got a minus a, which is delta with a 0 argument. And we know from the earlier slide that delta, when the argument is 0, we get the plus infinity. And that's exactly what we see here. We don't have to just shift it that way. We could shift it to the left as well, as I'll show in a moment. But before that, just to emphasize again, the area under this Dirac delta function remains equal to 1. And now, because we've shifted it to the right, therefore we've got this property here that it's plus infinity where x is equal to a. So hopefully all very obvious. But as I said, we could also shift it in a different direction. So I could do delta x plus b, and that would now move the delta function to where x is equal to minus b. Again, so we've got minus b plus b, delta of 0 is the plus infinity. So that's why the function shifts in that direction. We could also manipulate the amplitude. So remember what I was saying earlier about basis functions being parameterized. We've already seen one parameter, if you like, which is the shift position of the delta function. Another key parameter now is the amplitude, or if you like, the coefficient of the basis function, the delta function. So what I've done again is use that Gaussian definition here at the limit of the variance or the standard deviation tending to 0. And I've got the scale factor, the amplitude, the coefficient, just a factor of a there. So that happens to both sides. And so therefore now the integral of that delta function is just going to be equal to that coefficient or that amplitude. And so we can represent that as follows. So you can see here now that arrow function is not as tall as before. So my value of a here is less than 1, but of course it could be larger than 1, whatever we need in order to synthesize functions of interest, as we'll see in more detail in a moment. So then also I'm showing here we could of course still shift one of these scaled functions. So we've now got the same property here, that the integral of that shifted function is still equal to its coefficient a. And as before, we've still got the same property that it's plus infinity, if you like, at x equals a. But it's when you do the integral that we get that value of a. Okay, so just to summarize for the continuous definition of the delta function, we're using this expression here, delta brackets x for the continuous Dirac delta function, often represented by an arrow as shown here. There could be different types of arrowheads there, but hopefully you'll be able to figure out that it's the continuous Dirac delta. And then what I'm showing at the bottom here is just to emphasize again that any continuous function, in quantum mechanics that could be a wave function, but in signal processing it could be some arbitrary signal of interest that's considered to be a continuous function. And what we can do then, as I've shown earlier, is just now use those spike-like Dirac delta functions. Here I'm exaggerating their spacing a bit. They'd actually be infinitesimally spaced, so there'd be no visible gap between them. We can use them with various shifts. In other words, we can use that kind of x minus a, where a is just stepping through all the x values here, and then we could use a different amplitude, if you like, on all of them in order to recreate or synthesize some continuous function f of x. But we'll get back to that even more later in the video. Now I want to pick up on the discrete case, where we've now got some discrete Dirac delta function, which I'll be unpacking in more detail in a moment. But it's a very obvious generalization, or rather alternative description now in the discrete domain. So instead of having continuous x values, here I've got discrete integer values of x. So for example, from minus infinity to plus infinity, but only integers now rather than real numbers. And often we'll just use some kind of vertical line like this rather than the arrow notation used for the continuous case. And sometimes you might see a little circle on the top there. So you've got to look at the context to understand whether it's a continuous or discrete function, and for the delta as well. Okay, so just like we saw for the continuous case here, likewise for the discrete case, what I can do now is shift and scale or control them with amplitudes, these discrete delta functions, in order to create any arbitrary function of interest. I'm showing just positive values here, but they could of course be negatives as well. Okay, and then I'm showing here an example of what this sample value, this discrete function value, would be represented by. It would be a delta function, delta of x, shifted to x is equal to plus 3. Remember, we need that argument to be 0 to give us that unit value here of the delta function. And I'll be defining that in more detail in a moment. And then I can just control the amplitude with some coefficient a in this example. Okay, so let's get a bit more into the discrete delta function. Starting from the Kronecker delta function, named after a German mathematician, Leopold Kronecker. And so it's a very simple definition. Delta ij is equal to 1 when these two subscripts are equal, or equal to 0 when they're not equal. But in the context of signals, images, as described in this video, we'll be dealing with a simpler version, which is just defined as we've effectively seen on the previous slide, where we've just effectively got this, if you like, one-dimensional function, delta of n or delta of x. We should be able to change notation quite easily here, where it's just simply equal to a value of 1 when the argument, where the input is 0. So on the previous slide, that was when x was equal to 0. We get a value of 1 for the discrete delta function. And here, when n is equal to 0, we get a value of 1. Otherwise, we get a value of 0. And this will be variously named, this function, depending on the context. Nearly always, you'll do well if you just call it a delta function, and then in the context, it should be clear whether it's a continuous one or whether it's a discrete delta function. Sometimes called the unit impulse or even just an impulse function. That's very much in the temporal case, dealing with time signals like audio waveforms in digital signal processing. For spatial signals, for example, quantum mechanical wave functions, or for, in fact, this is a discrete case, so often this would actually be more like for an imaging context where we've got discrete images, where this would now be considered like a point source or a point. For the quantum mechanical case, it would be the Dirac delta function that would be used as a kind of idealized example of a completely localized particle. But for this discrete case, which is the practical case for digital signals and for medical images, imaging in general, we'll be considering the delta function as a point source or a point-like object that builds up your function, signal, or image of interest. Okay, so getting more into the detail again of that discrete delta function, which is like a special case of that Kronecker delta that we've just seen. Here I'm just plotting it again, showing n is equal to 0 as a value of 1. This is just a table of the values that the function takes on. So this is, you can see it's basically equal to 1 wherever the function has been shifted to. So if you have delta n plus 2, that means the delta of n has been shifted to minus 2, and so the value is 1, and then 0 elsewhere. And the rest of this table is fairly clear. I'll just plot an example or two here. So the one I just mentioned just now was delta n plus 2. And so sure enough, when the argument of the discrete delta is equal to minus 2, then that's where the value of 1 of the unit sample function, the discrete delta, has been shifted to, and it's 0 elsewhere. This again is the center case, which is that one there. So 0 everywhere except when n is equal to 0 for the no shift case. Or if it's shifted to the right by n is equal to plus 3, then we get delta n minus 3 shows that function a value of 1 at n equals 3 and 0 elsewhere. And so that's the example shown in the last row of that table. So hopefully this is all fairly obvious stuff, but very important to understand clearly. So as with the earlier case for the continuous Dirac delta function, we can use an amplitude or a coefficient to modify the height of this delta function. So here I'm using a capital A as a coefficient or an amplitude, a scaling factor. Earlier on I used a lowercase a. The point is we can use any coefficient we like, of course. And so what I'm showing here again is the original unmodified discrete delta function. Here I've chosen a value of a equal to 2. And so the function is 0 everywhere except for when n is equal to 0, and that value of 2 just means the height now is doubled. It's just a factor of 2 compared to the unit height for the unmodified discrete delta function. We could use negative coefficients or amplitudes. So I'm showing here a case of a delta function shifted to n is equal to minus 2. And now I've got a negative 1 in front here, and so that means that the amplitude of that is minus 1. So that's fairly obvious, I hope. And then one more example. I've shown here a delta of n now shifted to n equals plus 3, and now I've got a scaling, an amplitude or a coefficient of 1.5, and so the amplitude of that function is now 1.5 at n equals 3 only and 0 elsewhere. So the whole value of that is that now we can mathematically represent all kinds of signals of interest and indeed images as well. So I'll start off with just this simple 1D case. We've got some function. Now the function value is x, so you've got to watch out for changes of notation. So the function value x depending on some discrete integer variable n going from minus infinity to plus infinity. So we're going to express that discrete time signal as a weighted sum of those shifted discrete delta functions or impulses. Remembering, of course, that this could be an audio signal or indeed any signal of practical interest, such as sampled voltages from an ECG, whatever it might be. So how are we going to represent a discrete signal like that? Well, here is our function x of n, shown with various values. X here is negative, positive, and so on. It's a function of discrete integer index n, and we're saying that's equal to a whole summation of terms. And to understand the breakdown into those delta basis functions, what we can see here is that n equals -2, we've got some function value. And so what we've got here then is the function x evaluated at position n equals -2. So that's x brackets -2. That's the amplitude of the function. And that serves as a coefficient or an amplitude for simply the discrete delta function, delta n, shifted to that corresponding location, which of course we need to use n plus 2 to shift the delta to position -2. So that should be clear from all the earlier examples why the shift goes in that direction. And then the next sample here in this discrete function is the -1 here, where what we've got is the function x evaluated at n is equal to -1, and that in fact is a negative value here, and that serves now as a coefficient or an amplitude, a scaling factor for a delta function shifted to n is equal to -1. So let's make that general now. How do we go about doing a synthesis of a general function, discrete function, from delta functions? Well, all we do is take the function that we want to express as delta function. So here it's x of n. And what we do is just run through all the values of the function. So the function is x of n, but what we're going to have, if you like, is a marker to see where we are as we go through that function. And I'm going to use integer value k to slide from -infinity to +infinity to find the function value x, which depends on that independent variable k running from -infinity to +infinity. So we're going to visit different values of k, and for each one of them, as shown here, we're going to have a delta function, a discrete delta, which depends on some integer index n shifted to the position k of that x of k. So remember, k is our choice of position. We're getting the function value x, and then we're using that as an amplitude or a coefficient for the discrete delta, which has been shifted to the position of n is equal to k. And of course, we need to do that for all values of k. So I'm sliding k from -infinity all the way up to +infinity, visiting all the values of the function x of k, using those as coefficients for delta functions, which have also been shifted to all the possible positions from k equals -infinity to k to +infinity, which of course just corresponds to the shift position of the delta function. Once we've done that, then of course that's going to, when you add them all together, as depicted here, you add them all together, and that synthesizes, reconstructs, or recreates your original discrete function. So hopefully it's a very obvious kind of notation that we're doing here, but it's really important to understand it in this way because, again, it really helps with understanding Fourier analysis and Fourier synthesis, as we'll see in other videos. So one more note here is that k, remember, was my control index of my summation. I'm visiting the function at positions n equals k. And then I had a delta function which remained a function of n, and so therefore we also have a function of n being left on that left hand side. So when we sum over indices k, we don't expect them to see them on the left hand side, but the one that we didn't sum over, that we left here, is also of course what appears on the left hand side there. Always like a simple sanity check that you can do on these kinds of expressions. Okay, so that was a synthesis, which I've just summarized again at the top of the slide here. It's just your function is just a summation of delta functions shifted and scaled. That's all that's going on there. But formally, it's quite obvious what it is, the answer, but we need to look at how do we find those coefficients. Now, for the delta case, as I said, we just visit all the values of the function and plug them in. That's obvious. But again, we just want to formalize that because it's going to be very useful for understanding the case of Fourier basis functions, where we deal with sines, cosines, and complex exponentials. So let's also handle the delta case very carefully. So how do we find these coefficients x of k? Well, it's a very simple process. What we do is we take that original function, x of n, so I'm showing that here, x of n, and then if we want to find the coefficient for basis function delta n minus k, then all we do is multiply that original function by the basis function for which we wish to find the coefficient. Okay, so that should be obvious. We've got x of n, and then we just multiply it by delta n minus k. So that would be like saying, here's the function up here, there's x of n. If we wanted to find the coefficient for that delta function there, then all we do is multiply it by, imagine another axis here with a delta function just positioned at n is equal to plus k, so that would be delta n minus k, and you just multiply that by the signal, and of course then all it would do is pick out that value at position n equals k. That's what would happen. Once we've done that, in fact that would be good enough for the case of the delta function, but just to formalize what we do, we then have to sum over the function. Now of course when we've got a delta function, because it's 0 everywhere else other than where it's been shifted to, this actually makes no difference, but just to formalize the way that it's done, because that is what would be done when we come to complex exponentials, for example. And then we just, that will, in fact this is just so obvious, x of n multiplied by the delta function shifted to position n equals k. What that's going to do is just pick out that function value x evaluated at n equals k, and so that's exactly what we write on the left hand side here, and that is exactly the coefficient in the synthesis expression. Now again, I've taken a long time over that, because even though it's actually hopefully very obvious to you, I've taken a long time because I also want to point out that this is known as the sifting property of the delta function. In other words, the delta function, when multiplied by another function and then integrated or summed, will pick out the function value according to wherever that delta function has been shifted to. And in the context of where we're going later on in other videos, this is, if you like, a version of analysis. In other words, how do we analyze the function to find a coefficient for a basis function in order to resynthesize that same function. Okay, so this is just a quick reminder to say that we're talking about various digital signals of interest, whether it's a time activity curve in PET imaging, whether it's some digital signal, some audio waveform, and they can all be expressed in exactly the way that I've just talked about. Here it's just a synthesis, coefficients with shifted delta functions. Here's a temporal function, discrete time function. Again, it's coefficients with shifted delta functions, and likewise for this other example here. Notice again, we shouldn't get hung up about different notations here. Here I'm using x as the function value, but here it's the independent variable there. And then, for example, I've got f as the function value here and t as the independent variable. It should be obvious from the context of the equation what the independent variable is and what the function value is. So this is now a key summary slide where I really want to link together all that we've just been looking at. So for synthesis, we're saying a discrete signal or function, f of n, is a weighted sum of shifted delta functions, each of them having a coefficient c of k. So there's my delta n shifted to position n equals k. So just visualize a delta function shifted to n equals plus k. It has amplitude, or more generally we call it a coefficient, and that's just controlling the, if you like, the height of that delta function. And then what we do is just add them all together for all the different positions of the shift of the delta function k and all the respective coefficients for those shifted deltas. When you do that, you just synthesize your discrete signal f of n. Then we have the corresponding analysis equation, and that's all about saying the amount of each delta function, the amount of each basis function, can be found as follows. You take the function of interest, f of n, multiply it by the basis function for which you wish to find the coefficients. This is the basis function delta n shifted to position k. So k is, if you like, one of the parameters of that basis function. So you take your function, multiply it by the shifted delta, sum it all up, and that gives you the coefficient for that basis function that can be used in the synthesis expression. So you use that coefficient as the scaling factor or the amplitude for the shifted delta, add them all together to reconstruct the function. So these are fairly obvious equations, but really good to grasp, again, for the context of Fourier. And so, of course, for this case here, with delta functions as the basis functions, we get the very convenient relationship that C is equal to F. Okay, now to give you the continuous function analogies. Remember, we started out the video talking about the continuous Dirac delta function. So let's now revert back to that by using the synthesis and analysis expressions. So here now we're saying in the continuous case, we can reconstruct or synthesize a continuous function f of x by taking a continuous Dirac delta function. So now this would be the case for quantum mechanics, where we're often expressing continuous functions to express quantum mechanical wave functions. So we take that function, whatever it might be of interest, and we can express it as a delta function, delta x, shifted to a position x prime, and then what we do is we look at that function evaluated at position x equal to x prime and use that as a coefficient or an amplitude for that shifted delta. And you've got a sum over all the different positions in the function, and you've got to slide that delta to every single position in the function. You sum it all up, and then you reconstruct or synthesize the original function of interest. And then the analysis case, also known as the sifting property of the delta function, is where we say, well, to find that amount of a delta function that when added up can recreate your function, to find that coefficient, we use this sifting property, which is best explained as follows. You take your function f of x, if you multiply it by a delta function shifted to position x prime, then we know that that's going to be picking out the function value where x is equal to x prime once we've done the integral. Okay, so take the delta function, shift it to position x equals x prime. Remember, the delta is 0 everywhere else. And it's when we define it in the context of an integral, as I showed in earlier slides, and it's only when we integrate it that will then give us the finite result, which is the function value evaluated at x is equal to x prime. And that's exactly what we need in this synthesis expression. So just to finish on this slide, to say that all these concepts that I've been covering generalize in a very obvious way to the two-dimensional situation and even higher dimensional cases. We can have 2D delta functions, 3D, 4D, and so on. Here's just a repetition of the 1D case. Again, it's just saying a discrete function is a weighted collection of shifted delta functions. And in 2D, we'd say we've got a 2D function here. And again, it's just a particular coefficient for a delta function defined in two discrete dimensions now. So we have the delta function shifted to x equals k, and the delta function shifted to y equals L. And then we evaluate the function, the original function at position k and L. And that's the coefficient for that shifted delta function. We add them all together, and that reconstructs or synthesizes our original function. I do have another video where I'll be covering explicitly the example of the 2D delta function, so feel free to take a look at that to go into this example in even more detail. Thanks for listening.